Hello buddy, welcome. So today we're going to talk about mode group. Right. Because this is a very popular group and happens everywhere. Alright, so some people refer to it as most popularly referred to as, for example, Z mod NZ, where Z is of course the symbol for integer and N is some natural number, right, typically. Right, so Z mod NZ. I read Z mod NZ. We're going to talk about this group because it happens so many times and it's so useful. We're actually going to need it on the next problem we're going to solve. And maybe to think about it a little bit, right? So we're used to categorizing things all the time in the real world, right? We categorize things a lot in the real world. For example, let's say you could divide the set of all people into those who are tall and those who are short. Immediately you do that, you've got like a billion. Immediately we do that, we've got like a billion people, and some of them we'll call tall, right? So this symbol or this word tall represents all those people that we've put into this category, and then those whom we've defined as short fall into this category. And suddenly the entire universe of people has been broken down into two representatives, tall and short, right? Well, another one is, for example, we could think of another way to think of like the entire set of people is you could think of them in terms of happy and sad, right? So in essence what we've done when we do that is we've created a bucket. If you're happy, you fall into this bucket. So all the people who are happy fall into this bucket called happy. And all the people who are sad fall into this bucket called sad. And so the entire universe of people now has two representatives, happy and sad. This bucket here represents all those people who are happy. This bucket here represents all those people who are sad. So we've got something that's really huge. The set of all people is a billion. I think at least a billion, I'm pretty sure. Maybe China has like a billion people. So at least a billion people, and we've made them into just two things, happy or sad, right? So we use this concept a lot in the real world, the breaking up things into categories. And so we also do it in mathematics, right, with integers. Consider the set of integers, and that's what our mod group is all about. The set of integers, you start from 0, 1, 2, right? And you go on forever in the positive direction. -1, -2, and you go on forever in the negative direction. The set of integers is infinite, right? But we can break it down into categories as well. For example, we could get all this infinite set of integers and break it down into just two groups. We could break it down into the bucket. We can break it down into one bucket called odd. Right, this bucket is called odd. And then we could break it down into another bucket right here. We call this bucket even. Right? So even right there. Right? So when we do this, we've gotten the entire set of an infinite set of things and put it down into one bucket. One bucket we called odd, the other bucket we called even, right? So odd represents all those numbers that are odd, right? You could say maybe half of them. I guess you could say that. And even represents the other half, all of those that are even, right? So we've gotten something infinite and given it a finite sense. Right, we've ignored the difference between them and just put them into two different buckets, odd or even. Right. Well, how else could we categorize the integers? Well, we could refer to them as, say, 0, where we could create a bucket called 0, right, and another bucket called non-zero. Right. Not. This bucket is called not 0. Right. So obviously this bucket here contains one element, namely 0, and this one contains the rest. But in a sense, we've again gotten an infinite set and split it up into just two finite things, 0 or not 0, right? And of course there are many more we could do positive and not positive, right? But when we talk about the mod group, which is what we're talking about here, it's kind of the same, but what we do instead is we break down the set of integers into, in a sense, remainders. So for example, when we talk of, let's say, if we're working mod is short for modulo, right? Modulo. So maybe I write it there once for last time in my life, right? Hopefully in yours too. Mod is cooler. So mod, right? Let's say if we work mod 3. When we work mod 3, what we're saying is we're getting this entire universe of integers, and we're saying we are going to get every integer and divide it by 3. Well, there are only 3 possible remainder. Either it gives me 0, right? That means if I divide an integer by 3 and have a remainder of 0, it means 3 divides it, right? Or I could have a remainder of 1 and I could have a remainder of 2. These are the only possible remainders when you divide something by 3. And so when you work mod 3, what we've really done is we've now created 3 buckets. One bucket is called 0. The other bucket, I hope you're appreciating my artwork. The other bucket is called 1, right? And the other bucket is called 2, right? We've gotten the entire universe of integers and given it a finite sense, where we put all things that have a remainder of 1 are represented by 0. All things that have all things that have no remainder when divided by 3. All integers that have no remainder when divided by 3 are put into the bucket called 0. All those that have a remainder of 1 when divided by 3 are put in the bucket 1. And all those that have a remainder of 2 are put in the bucket 2. Right? And so, since every integer either gives remainder 0 when divided by 3, remainder 1 when divided by 3, remainder 2 when divided by 3, it means that we can actually put every integer into one of these 3 buckets. Right? It's just a way to reduce and represent everything. And of course, maybe I can ask you a basic question. What do you think working mod 4 does? Mod 4 does exactly what you expect, right? Mod 4 is going to divide the entire universe of integers into one bucket, right? Bucket 0, that is, you divide all the integers which when divided by 4 give you no remainder. That is, 4 divides them completely. Well, those are put into the bucket called 0. And then anybody who when divided by 4 gives me a remainder of 1 is put in the bucket called 1. Anybody who when divided by 4 gives me a remainder of 2 is put in the bucket 2. Everybody who gives a remainder of 3 is put in the bucket 3. Right? And so working mode 4 reduces the universe of integers into just 4 buckets. Everything is, so 0 is a representative of everything divided by 3. These are called representatives, right? Well, another way to write mode 4 is to think of it as Z mod NZ. In this case, it would be Z mod 4Z. Z mod 4Z is another way of writing mod 4, like thing of things mod 4. It's reducing the bucket to 4 things, right? If we were to reduce the bucket to 5 things, we'd say Z mod 5Z. All the integers, we divide them by 5 and we check the remainders. Obviously, we can ask what does the set Z mod 5Z stand for? Well, I mean, what elements are in the set Z mod 5Z? Clearly not all the integers. It's the buckets that we get all the integers in place. Well, it's gonna be all those things when divided by 5 that give me no remainder, that 5 divides completely. Well, 0 is, I would have a remainder of 0 when you divide integers by 5. The other possible remainder is 1. The other possible remainder is 2, 3, and 4. Right? Those are the only possible remainders. Right? Those are my buckets. So, in general, what we're saying, for example, is Z mod NZ what we're saying is that z mod nz equals to 0. You could have a remainder of 0. Here n is just any natural number, right? N is a natural number, right? So you could have 0, you could have a remainder of 1, you could have a remainder of 2, you could have a remainder of 3, you could have a remainder of 4, right? All the way till n minus 1, right? That's where it ends. That's what this set is. So while I'm writing them as 0, 1, it's really not the number 0. It's this 0 here represents all the numbers which when all the integers when divided by n give me no remainder, 0. Right? And so this is actually loaded. 0 is not just 0, it's like an infinite number of things. 1 is not just 1, it's an infinite number. But we just write it like this for convenience sake. So basically, well, why am I bringing this this weird setup, this set z mod nz? The reason I'm bringing it up is because z mod nz is actually, well, you guessed it, right? It's a group, right? Z mod nz is a group. For example, I'm gonna just start basic. Consider, say, let's look at the world mod 3z. Say, let's just mod 3. So let's consider z mod 3z, right? Z mod 3z. Well, what are the elements of z mod 3z? We have 0, we have 1, and we have 2, right? That's z mod 3z. Well, we could talk of addition of elements over here, right? So for example, well, 0 plus 1, for example, will just give me 1, right? So the addition really works the same way as you do. The only thing that happens is sometimes you go over. For example, 1 plus 2 suddenly gives me 3, right? And so notice 3 is not an element of the set, but 3 when divided by 3 gives me no remainder. That is, 3 divides 3, and so it falls into the bucket of things that have remainder 0. And so 1 plus 2 becomes 3, which is said to be, the symbol is congruent to 0, right? Mod 3, when you're working mod 3, it's congruent to, so it really becomes 0, right? Guess what 2 plus 2 is going to be? 2 plus 2 is going to equal to 4, right? That kind of makes sense. But 4 is not in this set 0, 1, 2. So to obtain what, we have to write 4 in terms of just these 3 categories. So we divide 4 by 3, and we see that the remainder is 1, and so 4 really becomes congruent to 1, right? So it falls into the bucket 1, right? And that's kind of how we do this whole thing. So right, and obviously the inverses make perfect sense, right? So for example, maybe let me work in z mod 5z for the time being. So let's try z mod 5z. Z mod 5z has the elements 0, 1, 2, 3, 4, right? These are the elements of z mod 5z. Well, I could ask myself, what's the inverse of 2, the additive inverse? Well, in this case, we could think of our identity as being 0, right? Remember, we want to see if z mod 5z is a group. Well, to be a group, remember what we need to check, right? Number 1 is closure. Number 2, we need to check identity, right? We need to check identity. Number 3, we need to check inverses. Number 4, we need to check associativity, right? So we're looking at z mod 5z under just addition, right? We're looking at z mod 5z under the operation of addition. The special addition I was talking about, where if you add, let's say, 4 and 4 and you get something that's not in the set, you divide by 5, and then you check what the remainder is, and you assign that to be the value. So, well, is the set closed is the question. Well, kind of makes sense, right? So if you add up 2 things in the set and you get something that's less than 5, then it just becomes that value. For example, what's 2 plus 3? Well, let's say 2 plus 2. 2 plus 2 equals to 4. right? And that becomes the value 4, because 4 is in the set, right? What's 1 plus 3 gonna be? 1 plus 3 is just gonna be equal to 4. Well, 4 is also in the set. 1 plus 1, for example, will equal to 2, exactly as we know how to do it. But now the question becomes, how about, say, 4 plus 3? Well, 4 plus 3 gives me 7, right? Well, 7 is not in the set. How am I going to find it? I'm going to get 7 and divide it by 5 and check what the remainder is going to be. And I realize that 7 divided by 5 gives me a remainder of 2. So this is congruent to 2, right? And so does it make sense then that any two elements that I add up in here, if I consider this thing of dividing them by 5 and checking remainders, I realize that if I add up any two elements, I always get an element in Z mod 5Z. So that means that Z mod 5Z is closed, right? What's the identity going to be under addition? It's going to be the sort of thing that if I add anything to it, I get that thing back. Well, what is that? Well, you guessed it right. It's 0, right? 2 plus 0 is 2. 1 plus 0 is 1. Exactly as expected. The identity is 0. How about inverses? Inverse means, remember, that if I get an element and I add it to its inverse, I must get the identity. In our case, we said the identity was 0. So for example, what number am I going to add to 2 in order to make it 0? Right? And remember, this is 0 in this special is mod 5, right? So, well, one thing I could do is, there's no minus 2 really in here, technically speaking. So I think of, like, if I add 3 to 2, I get 5. 5 is not in the set, but 5 divided by 5 gives me a remainder of 0. And so 2 plus 3 is really equal to 5, which is congruent to 0. And so 3 then, it's weird but it's true, 3 then is the inverse of 2. 2 inverse actually equals to 3, right? So that's kind of how inverses work here. So does it make sense then that every number, every value has an inverse? Let's try one more. Like, let's say 1. What's the inverse of 1? I think of something, when I add it to 1, I'm going to get 0. That's in this weird modular thing. Well, if I add 4 to this, I have 5. 5 divided by 5 is 0. And so suddenly we see that 1 inverse equals to 4. So that's kind of how it works. So the inverses work. Associativity works because addition behaves the same way as normal addition of integers, and we know that that's associative because we proved that the integers under addition are a group. So you see, Z mod 5Z is a group, and in general, really, Z mod NZ, for any n, Z mod NZ, as we saw before, well, it's the set consisting of the elements 0, 1, 2, 3, blah, 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 up to n minus 1, right? Those are the possible remainders that you can have. For any number in here, let's say you pick some number, we can prove easily that this is a group, right? The identity is clear, as we saw before, right? Because, once again, we need to prove that there's an identity. We need to prove that it's closed, right? This is the general case, Z mod NZ. We need to prove that inverses exist. We need to prove that it's associative, right? Here we're looking at Z mod NZ under addition, right? Well, notice 0 is the identity as seen before, right? Because anything plus 0 gives me that thing back. Identity has nothing. We have the identity. Well, associativity follows from normal addition of integers. Is it closed? Absolutely. If I get any number over here and add it, if the sum gives me something that's bigger than n minus 1, I just divide by n and take the remainder, right? So for example, maybe let's say I add two things here and I get something like n plus 2. Well, I'll just divide n plus 2 by n and realize that my remainder equals to 2, and so this will be congruent to 2 modulo n, right? So it's closed. Right? Closed. I add any two things, I get something back in there. Well, let's talk about inverses, right? Inverses is the other thing we need to think about. Well, just like before, if I pick any number in this list, for example, if I pick 2, I'm looking for something which, when I add to 2, I get an answer that's divisible by n. Because if it's divisible by n, then I'll get a remainder of 0 and to give me 0, right? Because I'm supposed to add 2 plus something to give me 0. Well, I'm going to add, for example, in this case, n minus 2, right? 2 plus n minus 2 gives me n. but n divided by n is 0, right? And so n minus 2 is really equal to 2 inverse, right? It's weird, but I hope it's making more sense, right? And so in general, if you pick any alpha that belongs to Z mod nz, any alpha that belongs to Z mod nz, what's alpha inverse gonna be under addition? Well, alpha inverse under addition, right, as you're guessing, it is gonna be n minus alpha. Why? Because alpha plus n minus alpha, right, is gonna give me alpha minus alpha is gonna give me 0, so now I have n, right? And n divided by n equals to 0, right? And so alpha plus n minus alpha is really congruent to 0, which would mean that n minus alpha is the inverse of alpha, right? So everything has an inverse, and the inverse is also an element in there, right? It kind of makes sense, doesn't it? So because alpha is at least 1, so n minus 1 is there, n minus 2 will be there, n minus anything really less than n is going to be in this set, because it includes everything 0, 1, 2, 3 up to n minus 1. Alright, so under addition everything makes sense, and there's also a multiplication, and the multiplication works exactly as you expect. For example, in this case, well, 3 times 4 say is going to be equal to the normal 12, but then we check again. Does 12 exist in this set? No. Divide 12 by 5 and check the remainder. In this case, the remainder will be 2. So 3 times 4 is equal to 12, which is congruent to 2, because 12 divided by 2 gives me a remainder of 2. And that's how the multiplication kind of works, right? So this group is really important because we use it a lot, right? It's the source of many examples. And later you'll find out that when the n is actually a prime number and you have something of the form pz, Z mod pz, where p is a prime number, then suddenly this thing here is not only a group, it's also something called a field. But you don't need to worry about fields yet. Fields will come later on. But one thing that it implies, for example, for a prime, it means that if you look at the elements, right, because we know that Z mod pz is going to equal to 0, 1, 2, 3, all the way up to p minus 1. With the exception of 0, we know that this is a group already under addition. But what you find interesting is that under multiplication, except for 0, every other element will have a multiplication inverse. That is, you multiply one element by another, you divide by p, and you get the answer as 1. But anyways, that's getting ahead of ourselves. Just remember, the most important thing is to remember that Z mod nz is a group, and you need to remember that multiplication makes sense. You just multiply two things, divide them by the modulo, for example p or n, and check the remainder, right? So thank you for watching this video, and hope to see you in the next one. Bye.